Okay. Hello, everyone. My name is Chen-Ming Wu. I'm from National Taiwan University. Today, I'd like to introduce a framework to evaluate the transition to aggregated convection. And I would like to provide examples with different microphysics scheme using the vector vorticity equation model, VVM. So what is convection aggregation? When you simulate the radial convective equilibrium in a cloud resolving model with fixed SST and large enough horizontal domain, and through long-term integration, the convection will develop into the aggregated state as shown in the animation below. This kind of aggregated convection has strong impact on the radiation. Hence, the focus, people study this impact of aggregated convection on climate sensitivities. Recently, Wing and al. 2018 and 2020 proposed a radial convective equilibrium intercomparison project. On the radial convective equilibrium, in a large enough horizontal domain, the model tends to develop convection aggregation as shown in the lower left panel. However, although the convection aggregate develop across the model, the convection structure varies among the models as shown in the lower right panel. And this has different convection structure has impact the climate sensitivity, even though the horizontal distribution SST is fixed. Another group of people think that the radial convective equilibrium should include the interactive SST. By doing so, the interactive ocean prohibits or delays the onset of the convection aggregation through processes such as the negative feedbacks of these convection SST feedbacks. Chen and Wu 2019 showed that in their cloud-resolving model simulations, the convection can develop into the aggregated state as shown in the lower right panel, or the non-aggregated state as shown in the lower left panel, with strong interaction of the SST. You can see that in the non-aggregated state, due to the envelope cloud effect, the SST can eventually increase to a 303 degree, while that the SST remains in a horizontal structure in the aggregated state. Based on the previous studies, we can imagine the convection aggregation is controlled by two dominant feedbacks. One is from the boundary layer processes, and the other one is from the free atmosphere. The boundary layer processes can be imagined as the convection SST feedbacks, in which the radiation interacts strongly with the SST, leading to different development of the convection. The other type of the interaction is the convection moisture feedbacks, as the convection tend to develop nearby the convective system, leading to the clustered convective system, and hence the development of aggregated convection. By analyzing the competing effects of these two processes, we can design a framework to evaluate a model toward the development of aggregated convection. So in this study, we use the VVM, the vector vorticity equation model developed by Jun and al. 2008, as a cloud resolving model to investigate this framework. The model is further developed by Wu and al. 2011 to include the topography, and the Wu and al. 2019 to involve the length average processes. The model is known for its prediction of horizontal vorticity, so that the model is responsive to the horizontal gradient of buoyancy as shown in the equation. The experiment used two different microphysics available in the model. The first one is the VVM link scheme, which is predefined categories as shown in the left panel. The other one is a P3 microphysics, which predicts the ice properties based on the ice itself. The major difference of these two schemes is that the mass weighted density can be very different in the P3 microphysics based on the physical processes. However, in the link scheme, the density will be defined by its own category. So let's introduce the framework. Following Chen 2019, we used the initial SST gradient as the environment for the convection moisture feedback. And we use the mixer depth as the environment for the convection SST feedback. As you can imagine, when you have stronger SST gradient, it's easier to develop the convection moisture feedback. On the other hand, when you have shallower mixer depths, the radiation can interact with the SST easier and lead to the stronger convection SST feedback. So we do numerous experiments on this diagram, and the results can be separated into aggregated state, as shown in the upper right corner, or the sporadic convection, as shown in the lower left corner. The results show that the sharp transition between the non-aggregated and aggregated state of the experiment. A clear bifurcation is demonstrated with this framework. On the other hand, if we use P3 microphysics, similar bifurcation diagram can be found, but the bifurcation line moved to a lower left panel of the diagram. This result suggests that the stronger convection moisture feedback in P3 compared to Vivian Lin. The framework highlights the importance of using a competing effect of physical processes to evaluate the different behavior of convection aggregation in the model. In this study, we further want to understand what happened to the P3 microphysics that can lead to the strong convection moisture feedback. So we do the furthermore static energy variance budget as shown below. The dominant process in the variance budget is shown in the convergence term here. There's a stronger convergence feedback in the P3 microphysics, suggesting that there is strong convection in P3. To support our hypothesis, we calculate the convective core clouds, which is defined by the convective cloud object with vertical velocity greater than 0.5 meter per second and a cloud base below 2 kilometers. Basically, we want to identify convective core in the convective systems. By calculating the probability distribution of the convective core clouds, we can see that in the P3 microphysics, there's tend to have larger convective core cloud occurrence in the P3 compared to the Vivian Lin. This is caused by the reduced melting effect associated with strong convective object in P3, as suggested by Huang and Wu 2020. Basically, it means that in the strong convective region, you can form hail instead of grapple, so that the hail can move faster throughout the freezing level. That's reducing the melting effect and sustain the stronger convective object to develop. Okay, here's a summary. This study introduced a framework to evaluate the transition to aggregated convection under radiative convective equilibrium simulations using VVM. And the key idea is to include the VVM with a mixed layer step ocean model. And this framework introduced the competing effect between the convection SST feedback and the convection moisture feedback by modifying the initial SST gradient and mixed layer depths. With the P3 and Vivian Lin, two different microphysics, we can see a clear bifurcation separating the aggregated and non-aggregated state found in both experiment sets. The bifurcation diagram is shown to be useful in identifying the dominant process in the model. The results point out that stronger convection moisture feedback in P3 compared with Vivian Lin is caused by the larger convective core cloud occurrence. Overall, the results suggest that the uniform view of the process-based evaluation of convection aggregation among various cloud resolving models that use different dynamics and physical parameterizations. Thanks for your listening. I'm here to take questions.